Okay, so let's go over the notes for today. We are going to be talking about standardizing our data and normalizing it in percentiles. And standardized scores is what allows us to compare things to each other when they have different distributions, for example. Most common thing would be if you wanted to compare your ACT score to your SAT score. They have different scales, so how do we go about comparing them? So that's what allows us to do this. And we're going to look at basketball players today as we do this. So a couple of things we need to note is what is a percentile? It is the percent of data below a certain data value. Okay, so if I said I'm in the 86th percentile, that means I have a higher score than 86% of the people who did whatever task it was. And at what percentile is the person who makes a salary of $43,000? And this is going back to the data from last time. So here are my salaries. So there's 43,000. So I'm going to block off the ones below it. I have 9 points below it. So 9 out of 12 is 75. So 43,000 is at the 75th percentile. I don't know how much above it is. It's just at the 75th percentile. And remember we had our box plot. This one was not to scale. We had to turn it sideways to make it fit because this is so far out here. And we had Q1, which remember Q1 represents the 25th percentile. So we say Q1, or the value of 34,000, is at the 25th percentile. What percentile is the median? So the median is at the 50th percentile. And what percentile is quarter three? Q3, that is at the 75th percentile. And again, it's at is how we use it. It is at the 75th percentile. Okay, so here we've got two people who've taken the SAT, one's taken the SAT, one's taken the ACT. This is one of the guys who teaches AP stats, so he made this up. So that's him. And he scored, at least what he's telling us, a 1050. Guy Ferrari, anyone like Guy Ferrari? He scored a 23. And if we want to compare them, I have to see what percentile they are. So our stats teacher, his score was in the 45th percentile. Guy Ferrari's ACT score was in the 69th percentile. So relative to their respective measures, Guy Ferrari's score is relatively more impressive because he scored above 69% of those who took the ACT, whereas our AP stats teacher scored above 45% of the people who took the SAT that year. Okay, let's continue on to the next page. We want to talk about relative frequencies here. And so what we've got here is the ACT scores. The maximum is a 36. And if we want to look at this, so the total of all the people who scored a 10, an 11, a 12, blah, 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 all of them would be at 100%. So I wanted to see a score of 18, so I'd come here, come up here, and that is at the cumulative frequency of 40%. Or in other words, a relative, if you score an 18, you're at the 40th percentile. You've scored better than 40% of the test takers. If I wanted to see, let's say you're applying for an elite college and want to score in the top quartile, so that's the top 25%, that means I need to be looking at the 75th percentile. So I would come over here, 75th percentile, and then drop perpendicular down. Let's see how straight I can make this. Should be right here. Need a better pen there. So if I want to score better than the 75th percentile, I drop down and I see that the ACT score be a 24. That is at the 75th percentile. So I would have to score a 24 or better to be in the top 25% of students. So this is cumulative frequency. Again, the percent of people who scored a 10 looks like it's just barely above 0, which is good. 11, same thing. 12% now, we've got a little bit of a difference here. The difference from here to here in terms of the height is what percentage scored a 12. The difference from here to here in height is how much percentage. And we just keep adding all those percentages together, which is why you have to end up at 100%. These are all the possible values because we don't have people scoring way down here. Okay, we want to standardize our scores. So z-scores, you're going to hear about z-scores a lot. This is the same as standardizing scores, but it measures how many standard deviations a data point is above or below the mean. Okay, so we're dealing with numeric data, obviously, and I want to know how far away from the mean I am. And the z-score gives me a measure so I can compare things. So the way we calculate a z-score is you take your individual data point, so we call that x sub I, minus the mean, and this is the way we say this is mu. Mu is how it's pronounced, a Greek letter, gives us the standard deviation. And we use this funny little symbol here for standard deviation. Again, another Greek letter here. So our z-score is equal to the individual data point minus mu, which is your mean, divided by the standard deviation. And I'm actually going to come back to this page. Let's come to the next page. We're going to compare some great basketball players. We want to know who is the greatest of all time. Is it Wilt Chamberlain, played in the 60s, Michael Jordan in the 90s, LeBron, who's still playing, even into the 2020s. And here's the average points per game they had. So Wilt had 30.1, awesome. Michael Jordan had 30.1, and LeBron had 27.1. If we were just looking at those values, we would have to say there's a tie between Wilt and Michael Jordan. But we want to figure out who was the best. And to be able to compare them, I've got to look at what kind of distribution did we have in the 60s? What was our distribution in the 90s? And what was the distribution in the 2010s to compare them? So I'm going to find my z-scores, which will enable me to compare. So the mean, mu, of points per game in their era when they played, so the mean for Wilt Chamberlain in the 60s was 10.8. That was the mean for all players. The mean when Michael Jordan played was 8.7. So already it's looking like Michael Jordan is higher than Wilt Chamberlain is. He's farther away from our mean. And LeBron James, he's pretty far away from the mean also, because the mean when he's playing was 8.4. My standard deviation now during this era was 7.0 for Wilt, 5.9 for Michael Jordan's time, and 5.5 for LeBron. Now calculating the z-score, remember the z-score is x sub I, so my individual person, which was Wilt Chamberlain, was 30.1, minus the mean, so 10.8, divided by the standard deviation. So this gave me a z-score, and we just say z equals 2.757, typically round to one decimal place. But that will give me enough information right now. Sometimes we'll do 2, but approximately 2.8. And this is how many standard deviations Wilt Chamberlain was above the mean, basically. So that's what a z-score tells you. Michael Jordan, again, the individual data point minus the mean for his era, divided by the standard deviation for his era, and we get a z-score of 3.6. And finally, for LeBron, same thing. We take the individual data point minus the mean divided by the standard deviation, and we get 3.4. Remember, these z-scores tell me how many standard deviations each player was above the mean for their time period. So we're looking for which player was the highest, furthest away from the mean. So this would be Michael Jordan. He was 3.6 standard deviations away from the mean. So if we fill this in, Michael Jordan's points per game was 3.6 standard deviations above the mean for his era, making him the most unusually high scorer out of these three great players. There's lots of other great players out there, but here's just 3 particular ones that we used. So I want to come back now to that previous page to talk about this. And here we have 2 different distributions. They both have the same mean. So the distribution is under this curved line. So they have the same mean. But if I scored 14, is that better for group A or group B? Notice group B, the data is spread out more. So if you score a 14 here, you're better than, or there's 16% of the people are better than you. Whereas in this one, you're 2 standard deviations above the mean, so there's only 2.5% of the people scored better than you. So a player in League A who scores 14 is a better player than a player in League B who scores 14. Because in League B, there is a lot more players who are still better than you. I know it's a little confusing, but this is why when we standardize, it's important not just to looking at the mean or the center, but we also need to have the standard deviation included, because that gives us a measure of the variation of our data and how far it's spread out. So z-scores allow us to compare or standardize it, so we can look across different distributions. Okay, so coming back over here, we've gone through and done our 3 players, and notice quite a difference in the standard deviations. So even though the means were the same, even though the individual data points were the same, because the means were different and your standard deviations were different, we got different z-scores for them. And so that's how we came up with Michael Jordan was the best, or the greatest of these 3. Okay, how about this guy, Adam Morrison? He was not a great player. He played a total of 44 minutes in a season. So not a great player. He played on the Lakers in the 90s, I believe it was. And he averaged 2.2 points per game. But the league average was 8.4, and the standard deviation was 5.5 while he was playing. So if I calculate his z-score, so his individual points per game was 2.2. That doesn't really look like a 2. Minus the mean, or the mu, divided by the standard deviation. And we get a negative value. So a z-score of negative 1.3. This means that he was 1 point, oops, I must have calculated that wrong. Let's pause for a second. Let me fix that. Okay, that was a typo on my part. So the z-score should have been negative 1.12, which is approximately negative 0.11. Negative 1.1. So his z-score tells me, because it's negative, he was below the league average of in his era. Okay, so positive and negative z-scores, important things to keep in mind. If your individual data point is greater than the mean, so it's larger, then you have a positive z-score. If your individual data point is less than the mean, then you're going to have a negative z-score. Positive means that z-score gives you the number of standard deviations above the mean. A negative z-score tells you the number of standard deviations below the mean. Okay, and your discussion question, or for you to think about now, is why isn't the maximum ACT score 36 at the 100th percentile? And it's simply because it tells us the amount that is greater than. So you cannot be greater than yourself. So there is a slight number out here that are greater, that would score the 36. Okay, hopefully this helped a little bit. And take a look at the Desmos activity before you take a look at the homework. Okay, have a good day.